Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the strange and beautiful world of quantum physics, a place where certainty softens, particles behave like whispers, and reality itself may not fully settle into shape until it is observed. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little corner of space and time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into quantum physics together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Most of your life has probably felt reasonably predictable. If you drop a spoon onto the kitchen floor, it falls downward. If you switch on a lamp, light fills the room. Morning arrives after night with such consistency that you rarely stop to question it. The universe, at least from the scale of ordinary human life, appears calm, orderly, and dependable, like an enormous machine quietly turning its gears somewhere behind the curtain of existence. For centuries, this view of reality felt not only reasonable, but complete. The planets moved in predictable paths. Apples fell from trees. Ocean tides rose and fell with elegant rhythm. Even the motion of cannonballs and comets could be described with astonishing accuracy through mathematics. The universe seemed to obey rules with almost comforting reliability. It was the kind of reality you could trust. By the 1700s, Isaac Newton's laws of motion had transformed physics into something almost magical in its precision. Scientists began imagining the cosmos as a gigantic clock, vast, intricate, and perfectly measurable. If you knew the position and motion of every object in the universe, perhaps you could predict the future itself. Every sunrise, every storm, every heartbeat, every drifting planet. Reality appeared fixed, solid, definite, and for a while, it worked beautifully. You can almost picture the confidence of that era. Scholars sitting beneath candlelight with stacks of papers and brass instruments, believing they were steadily decoding the machinery of existence itself. One equation after another, one mystery after another falling quietly into place. The universe was becoming understandable, but beneath that confidence, tiny cracks had already begun to form. At first they were easy to ignore, little inconsistencies, small experimental oddities, faint hints that nature was not behaving quite the way classical physics expected, like tiny ripples disturbing the surface of an otherwise calm lake. And the strange thing about ripples is that they spread. Toward the end of the 19th century, physics stood at what many believed was the edge of completion. Some scientists even suggested there was little left to discover beyond refining measurements to a few more decimal places. Imagine that for a moment. Humanity standing confidently at the shore of knowledge, believing the great mysteries of reality had nearly all been solved. And then the universe quietly smiled and began behaving very strangely. It started with light. Now, light feels familiar to you. It spills through windows in the morning. It glows from phone screens late at night. It dances on water and flickers in candles. You rarely stop to think about how strange light truly is. But physicists did. For centuries, light had been understood mainly as a wave, like ripples moving across the surface of a pond. Thomas Young's famous experiments with interference patterns had made that seem undeniable. Light spread out, overlapped, interfered with itself. Simple enough. and yet certain experiments refused to cooperate with that picture. In some situations, light behaved less like a smooth flowing wave, and more like tiny packets, small bursts of energy arriving almost like invisible grains of rain. At first, this made little sense. How could something be both continuous and separate? Both wave and particle? The very question sounded almost absurd, like asking whether music was made of flowing melodies or individual notes. The answer somehow appeared to be both, and physics was beginning to realize that nature did not care very much about human intuition. That realization would slowly grow into one of the most profound revolutions in scientific history. Quantum physics, a field so strange that even many of the scientists who built it struggled to fully accept its implications. A world where particles can exist as possibilities instead of fixed objects, where uncertainty is woven into reality itself, where emptiness is never truly empty, where observation seems to influence outcomes, and where the universe beneath its calm surface hums with probabilities instead of certainties. But tonight, there's no need to rush toward the strangest parts just yet. For now, it's enough simply to notice the feeling that something beneath ordinary reality had begun to shift. The old clockwork universe was no longer perfectly smooth and predictable. Tiny fractures had appeared in its foundations, small enough at first to overlook, but impossible to ignore forever. And perhaps that is part of what makes quantum physics feel so strangely human. It reminds us that reality is not obligated to fit neatly inside the limits of common sense. The universe was not designed around human comfort. Our brains evolved to throw spears, build fires, recognize faces, and avoid danger beneath ancient night skies. Not to intuit the hidden behavior of atoms or the strange mathematics of probability clouds. And yet, here we are, tiny conscious creatures on a small planet, trying to understand a universe that becomes stranger the more carefully we observe it. Like someone staring into mist, only to realize the mist itself is staring softly back. Somewhere deep beneath the world of solid tables, drifting clouds, ticking clocks, and distant stars, another layer of reality waits quietly, a layer where certainty softens into possibility, where nature behaves less like a machine and more like a song still deciding how it wishes to end. And the deeper physicists looked into that hidden world, the more reality itself began to blur around the edges. As the old image of the universe begins to soften, that great cosmic clock of perfect certainty, another quiet problem slowly emerges from the shadows, not from distant galaxies or mysterious black holes, but from something surprisingly ordinary. Warmth, the gentle heat from a fireplace, the orange glow of a stove coil, the soft light of a candle flickering beside a bed late at night. Simple things. And yet, hidden inside these familiar comforts was a puzzle powerful enough to crack open the foundations of physics itself. By the late 1800s, scientists had become remarkably skilled at understanding energy, motion, electricity, and light. Equations seemed capable of describing nearly everything the physical world could do. There was a growing confidence that nature, however vast, ultimately obeyed elegant and understandable laws. But then physicists began asking a deceptively simple question. Why do hot objects glow the way they do? If you heat a piece of metal slowly, it first becomes warm but dark. Then, as the temperature rises, it begins glowing a dim red. Hotter still, it turns orange, then white, and eventually bluish-white at extreme temperatures. You can see this yourself in fireplace embers, old-fashioned light bulbs, or the coils inside electric heaters. The hotter the object becomes, the more energy it radiates as light. Straightforward enough. But when scientists tried to calculate exactly how this glow should behave using classical physics, something went terribly wrong. The equations predicted that hot objects should release more and more energy at shorter and shorter wavelengths. In theory, the amount of energy should rise endlessly toward the ultraviolet part of the spectrum, infinitely. A heated object, according to the mathematics, should pour out limitless ultraviolet energy, enough to completely violate reality as anyone had ever observed it. But real objects did not behave that way. A stove did not explode into infinite radiation. Candles did not vaporize rooms with invisible ultraviolet light. The universe itself stubbornly refused to follow the prediction. Physicists eventually gave this embarrassing contradiction a dramatic name: the ultraviolet catastrophe. And catastrophe truly was the right word for it, because this was not a tiny error buried in the decimal points of some obscure equation. It was a deep fracture in the logic of classical physics itself. Nature and mathematics were disagreeing. Imagine building a beautifully crafted map, only to discover that entire continents are missing from it. That was the feeling beginning to spread through physics at the time. The old framework still worked wonderfully for planets, bridges, falling apples and moving trains, but somewhere deep beneath ordinary reality, it was starting to fail, quietly at first, then unmistakably. Into this growing confusion stepped a German physicist named Max Planck. Planck was not trying to overthrow physics. In many ways, he was conservative and cautious. He hoped to repair the problem without disrupting the foundations of classical science. But sometimes the universe leads people somewhere unexpected. In 1900, Planck proposed a strange mathematical solution. What if energy did not flow continuously like smooth water from a faucet? What if it came in tiny separate packets instead? Little bundles of energy, tiny indivisible units, quanta. At first, this idea was introduced almost reluctantly, like a temporary trick to make the equations work. Even Planck himself did not fully realize how revolutionary it would become, but his solution matched experimental results beautifully. Suddenly, the ultraviolet catastrophe disappeared. The impossible infinity faded away. Nature behaved sensibly again, but at an extraordinary cost. Because if Planck was correct, then the universe was not continuous in the smooth classical way scientists had imagined. At microscopic scales, reality seemed grainy, discrete, almost pixelated in a strange cosmic sense. Imagine listening to rain on a rooftop from far away. At a distance, the sound feels smooth and continuous, almost like flowing static. But move closer, and you begin hearing the individual drops, separate impacts hidden inside what once seemed seamless. Quantum theory suggested something similar about energy itself. The universe, beneath its flowing appearance, might be built from tiny indivisible exchanges, and once that idea entered physics, everything began to change. It is difficult to overstate how unsettling this was. For centuries, continuity had felt natural. Motion appeared smooth. Waves flowed continuously. Heat spread gradually. But now nature seemed to whisper that beneath the surface there were boundaries, limits, smallest possible exchanges, not unlike notes in music. A melody may sound smooth as it drifts through a quiet room, but underneath are individual vibrations, distinct tones separated by tiny intervals. Without those separate notes, the music itself could not exist. Planck had accidentally discovered one of the universe's hidden rhythms, and even stranger discoveries were waiting nearby. Because once scientists accepted that energy might come in packets, they began revisiting old mysteries with fresh eyes, especially the mystery of light itself. Was light truly a wave, or something stranger? The answer would arrive through another quiet revolution, one that would transform a young patent clerk named Albert Einstein into one of the most famous scientists in history. But before we wander there, it's worth pausing for a moment beside Planck's discovery. There is something oddly beautiful about the way quantum physics was born, not through explosions or giant machines, but through humble observation. Warm metal glowing in darkness, firelight flickering softly against walls, scientists staring at ordinary heat and realizing the universe was hiding impossible secrets inside the most familiar things imaginable. And perhaps that is one of the gentlest lessons quantum physics offers us. Reality does not always reveal its mysteries in distant galaxies or violent cosmic events. Sometimes the deepest truths are hidden in the quiet glow of everyday life, waiting patiently for someone curious enough to notice that the light does not behave quite the way it should. The old clockwork universe had not shattered all at once. It had simply begun to flicker at the edges, like a candle wavering softly in a darkened room. The strange little idea introduced by Max Planck did not remain small for very long. At first, many physicists treated quanta almost like a mathematical convenience, a temporary patch placed over an inconvenient crack in the equations. Useful, perhaps, but not necessarily fundamental. After all, classical physics had worked so beautifully for centuries that few people were eager to abandon its comforting certainty. And yet, the deeper scientists looked into light itself, the stranger things became. Light had always occupied a curious place in human imagination. It feels so immediate and familiar. It spills across wooden floors in the morning. It filters through curtains. It dances on lakes and glows softly through clouds at sunset. Entire civilizations once worshipped the sun as a divine force because light seemed inseparable from life itself. And scientifically speaking, light already appeared well understood. By the late 19th century, experiments strongly suggested that light behaved as a wave. It spread outward, bent around corners, and produced delicate interference patterns when two beams overlapped. You can picture waves moving across water, one ripple meeting another, merging into larger crests in some places and cancelling into calmness in others. Light seemed to behave the same way. This understanding was elegant, comforting even. The universe once again appeared smooth and continuous. But nature, as physicists were slowly learning, has a habit of quietly undermining certainty. One experiment in particular began causing trouble. It involved shining light onto metal surfaces and observing what happened to the electrons inside them. Today this phenomenon is called the photoelectric effect, though the name sounds far more intimidating than the actual setup. In essence, scientists noticed that certain kinds of light could knock electrons free from metal, almost like tiny invisible impacts. At first glance, this seemed perfectly ordinary. If light is a wave carrying energy, then brighter light should deliver more energy to the metal, and if enough energy accumulates, electrons should eventually break loose. Simple. Except that is not what happened. No matter how intense some forms of light became, electrons refused to emerge unless the light reached a certain frequency. Dim blue light could eject electrons immediately, while extremely bright red light sometimes failed completely. This deeply confused physicists. Imagine turning up the volume on music louder and louder, expecting a glass to eventually shatter, only to discover that volume is not the important factor at all. Instead, the glass only responds to a certain pitch. That was roughly the situation facing physics. The brightness of light, which seemed like it should matter most, was not the deciding factor. Frequency mattered instead, and classical wave theory struggled badly to explain why. Then, in 1905, Albert Einstein proposed something radical. Perhaps light itself came in packets, not just energy in general, but light specifically. Tiny concentrated bursts. Today we call them photons. Einstein suggested that when light strikes a metal surface, each photon behaves almost like a small delivery of energy. If a photon carries enough energy, an electron is released immediately. If it does not, no amount of weighting or brightness helps. Suddenly the puzzle made sense, but the implications were astonishing. Because light, which had behaved so convincingly like a wave, was now also behaving like a particle. Not metaphorically, literally. A wave and a particle at the same time. This was one of the first major signs that quantum reality would refuse to fit inside ordinary categories. Nature did not seem interested in choosing between wave or particle. Somehow, impossibly, it behaved as both depending on how you interacted with it. And the deeper scientists explored this dual nature, the stranger it became. Imagine standing beside the ocean at night. From far away, the waves feel smooth and continuous, rolling toward the shore in broad, flowing patterns. But now imagine that each wave could also arrive as tiny individual droplets, separate yet connected to the larger motion. It sounds contradictory because human intuition expects objects to belong clearly to one category or another. A thing should either be solid or fluid, continuous or separate, here or there. Quantum physics was beginning to suggest that reality itself might not obey such neat boundaries. Even Einstein, despite helping launch this revolution, found many of its implications deeply uncomfortable. He admired the mathematical power of quantum theory, but resisted the idea that nature might fundamentally operate through probabilities rather than certainties. And in fairness, the universe was becoming increasingly difficult to picture clearly. Particles behaved like waves. Waves behaved like particles. Certainty softened into likelihood. Solid objects became fuzzy probability patterns beneath the surface. It was as though physics had wandered into a dream where familiar categories slowly dissolved at the edges, and yet the mathematics worked beautifully. Again and again, experiments confirmed these strange predictions with extraordinary precision. Quantum mechanics was not vague mysticism or poetic imagination. It was measurable, reliable, predictive, even when it violated ordinary common sense. That tension became one of the defining emotional experiences of modern physics. The equations worked perfectly. Reality itself simply refused to feel intuitive anymore. And perhaps that discomfort tells us something important. Human intuition evolved for survival in forests, plains, and ancient campsites beneath the stars. Our ancestors needed to judge distance, recognize movement, avoid predators, and throw stones accurately. Nothing in human evolution prepared the brain to intuit the behavior of photons, electrons, or probability waves. The microscopic world is not obligated to feel familiar to creatures built for the middle scale of reality. And still, there is something strangely beautiful about that realization. The universe is larger than our instincts, richer than our categories, more fluid than our language. Beneath the calm appearance of ordinary life, light itself carries a hidden dual nature, behaving not as one thing or another, but something softer and stranger in between, like mist illuminated by moonlight, refusing to fully settle into shape. And somewhere ahead, another experiment waited quietly in the wings, one even stranger than the photoelectric effect, an experiment so unsettling that it would force physicists to question not only what light is, but whether reality itself remains definite when nobody is looking. By the early years of quantum physics, scientists had already begun feeling the ground shift beneath their understanding of reality. Energy came in tiny packets. Light behaved both like a wave and a particle. Certainty itself was beginning to soften around the edges. Still, many physicists hoped these odd behaviors might remain confined to isolated situations. Perhaps the universe was only slightly stranger than expected. Then came an experiment so simple in appearance and so unsettling in implication that it would become one of the most famous scientific demonstrations ever performed. The double slit experiment. Its setup is surprisingly modest. Imagine a wall with two narrow openings cut into it, standing in front of a screen. Now imagine shining light toward those openings so the light passes through the slits and lands on the surface behind them. At first, physicists expected something straightforward. If light behaves like tiny particles, like microscopic grains of sand, then each photon should pass through one slit or the other. The pattern on the screen would simply form two bright regions directly behind the openings. Simple. But that is not what happened. Instead, the screen displayed an interference pattern. Bright and dark bands spreading across the surface like overlapping ripples on water. Some regions became brighter where waves reinforced each other. Other regions dimmed where the waves cancelled out. The pattern looked unmistakably wave-like. It was as though each photon had somehow spread itself out, travelled through both slits simultaneously, and interfered with itself before arriving at the screen. Already strange. But physicists pushed the experiment further. What if the light source became extremely dim? So dim that only one photon passed through the slits at a time. Surely now the interference pattern would disappear. A single particle could not interfere with itself, could it? And yet, over time, the same wave pattern slowly emerged, one tiny dot at a time. Each photon appeared individually on the screen like a soft grain of rain landing on glass, but collectively those dots gradually built the same interference pattern as before, as though every photon somehow explored multiple paths at once, as though possibility itself moved like a wave. You can almost feel the discomfort this created for physicists. The experiment did not merely challenge old assumptions, it challenged the very idea that particles travelled along definite paths when unobserved. And then the experiment became even stranger. Scientists decided to place detectors near the slits to observe which opening each photon actually passed through. A reasonable thing to ask. Surely the photon must choose one slit or the other. But the moment the measurement was made, the interference pattern vanished completely. Now the photons behaved like ordinary particles again, forming two simple bands behind the slits. Observation had changed the outcome. The very act of measuring which path the photon took appeared to alter its behaviour. For many people encountering this idea for the first time, the natural reaction is disbelief. It almost sounds poetic rather than scientific. As though reality becomes definite only when someone looks at it. But quantum physics is rarely quite that simple. In popular culture, this experiment is sometimes described in mystical ways, as though human consciousness magically creates reality. The actual physics is more subtle, and in many ways more interesting. In quantum mechanics, observation does not necessarily mean a conscious mind watching events unfold. It usually means interaction. A detector, a measuring device, a physical exchange of information, something interacting with the system strongly enough to reveal a definite outcome. Even a tiny interaction can matter. A stray photon, a nearby particle, a measuring instrument quietly recording information. The quantum world is extraordinarily delicate. Before measurement, the photon behaves according to what physicists call a wave function, a mathematical description containing many possible outcomes at once. The photon is not neatly travelling through only one slit in the classical sense. Instead, its possibilities spread outward like overlapping ripples. But once measurement enters the picture, those possibilities narrow into a definite result. At least that is what appears to happen. And the unsettling truth is that physicists still debate exactly what this means. even now, more than a century later. The double slit experiment remains one of the deepest mysteries in science because it forces us to confront an uncomfortable possibility. Reality at microscopic scales may not behave like a collection of tiny solid objects moving predictably through space. Instead, nature may exist in a softer state of probabilities and possibilities until interactions gradually pull those possibilities into definite outcomes. The universe, beneath ordinary appearances, may be less like a machine and more like a constantly unfolding negotiation between potential and certainty. Imagine walking through heavy fog at dawn. Far away, shapes blur together. Trees dissolve into mist. Paths remain uncertain. But as you move closer, details sharpen. Possibility condenses into clarity. Quantum reality feels strangely similar. Before measurement, nature behaves almost like a fog of overlapping futures. Measurement does not necessarily create reality from nothing, but it seems to force one outcome into focus while the others fade from view. And perhaps what makes this so emotionally powerful is how deeply it challenges human instinct. We are accustomed to believing the world exists in fixed detail whether we observe it or not. A chair remains in the room after you leave. A mountain remains standing overnight. The moon does not vanish because clouds cover it. At ordinary scales, this assumption works beautifully. But deep in the microscopic world, certainty appears less absolute. And that realization disturbed even some of the greatest physicists in history. Albert Einstein famously resisted the idea that probability lay at the foundation of nature. He once remarked that he could not believe the universe played dice. Yet experiment after experiment continued supporting quantum predictions with astonishing accuracy. Nature, it seemed, was under no obligation to behave according to human comfort. Still, there is something oddly calming hidden inside this strangeness. The double slit experiment reminds us that reality is not frozen and rigid beneath the surface. The universe is dynamic, fluid, responsive. Beneath the stable world of tables, walls, and drifting clouds lies a deeper layer where possibilities overlap softly like waves in moonlit water. And the closer physicists looked into that hidden layer, the more difficult it became to separate observation from reality itself. After the strange revelations of the double slit experiment, physics found itself standing in unfamiliar territory. Particles no longer behaved like tiny billiard balls moving neatly through space. Observation seemed entangled with outcome. Possibility itself appeared to spread and overlap like ripples across water. The deeper scientists looked into matter and light, the less reality resembled the solid mechanical universe people once imagined. And so physicists faced an enormous question. How do you mathematically describe something that does not seem fully definite? How do you describe a particle that behaves partly like a wave, partly like a localized object, and somehow exists among many possibilities before measurement? The answer arrived through the work of an Austrian physicist named Erwin Schrödinger. In the 1920s, Schrödinger developed one of the central mathematical tools of quantum mechanics. Today it is known simply as the Schrödinger equation, though beneath that formal name lies something surprisingly poetic. Because at its heart, the equation does not describe certainty. It describes possibility. Rather than telling us exactly where a particle is at every moment, quantum mechanics provides something softer and stranger, a wave function, a mathematical object that describes all the possible states a system might occupy. And already, you can feel how different this is from classical thinking. In classical physics, a planet has a precise position whether or not you look at it. A train moves along a definite track. A thrown baseball follows a predictable path through the air. If you know enough information, you can calculate where these objects will be later with remarkable accuracy. But quantum particles refuse to cooperate with that kind of certainty. Instead of existing as tiny fixed points hidden somewhere in space, they behave more like clouds of probability, regions where outcomes are more likely, and regions where they are less likely. Imagine walking through heavy snowfall at night with a flashlight. The air ahead of you is filled with drifting flakes, swirling unpredictably in the beam of light. You cannot point to one exact location and say with certainty where every snowflake will move next. But you can describe patterns, densities, likelihoods. Quantum mechanics works in a somewhat similar way. The wave function does not tell us exactly what reality is doing beneath the surface. Instead, it gives probabilities for what reality might reveal when measured. This was a profound shift in human understanding. The universe at microscopic scales no longer behaved like a fixed script already written in stone. It behaved more like unfolding possibility, and strangely enough, the mathematics worked beautifully. The Schrödinger equation allowed physicists to predict the behavior of atoms with extraordinary precision. It explained how electrons arrange themselves around nuclei, why atoms emit specific colors of light, why chemistry itself behaves the way it does. All of modern electronics, computers, chemistry, and much of modern technology quietly rest upon these quantum foundations. And yet, despite its incredible success, the picture it paints of reality remains deeply strange. Because according to the wave function, an electron orbiting an atom is not really orbiting in the classical sense at all. You often see atoms drawn like miniature solar systems, electrons circling the nucleus like planets around the sun. It is a comforting image, familiar, easy to visualize, but it is also misleading. In quantum mechanics, electrons behave less like tiny planets and more like diffuse probability patterns spread around the nucleus. The electron does not travel along one precise path hidden from view. Instead, its possible locations form what scientists sometimes call a probability cloud. A cloud, not a solid orbit. This means that before measurement, the electron is not sitting quietly in one exact location waiting to be discovered. Instead, reality itself appears distributed across many possibilities simultaneously. You can think of it almost like hearing music drifting from another room. The melody fills the space softly. You cannot point to one exact location where the song exists. It spreads outward as a pattern. Only when interaction occurs, when sound reaches your ears, does the experience become specific and immediate. Quantum particles behave in ways that feel similarly distributed and fluid. And perhaps the most unsettling part is this. The wave function evolves smoothly and predictably over time according to the Schrödinger equation until measurement occurs. Then something abrupt seems to happen. Possibilities collapse into outcomes. The probability cloud condenses into a specific result. An electron appears here instead of there. A photon lands in one spot on the screen. One possibility becomes real, while countless others vanish from observation. Or at least, that is how it appears. This strange transition between possibility and certainty became one of the deepest mysteries in all of physics. Because while the mathematics predicts outcomes astonishingly well, physicists still debate what the wave function actually represents. Is it physically real? A genuine structure underlying reality itself? Or is it merely a tool for organizing information and predicting measurements? Even today, no consensus fully exists, and perhaps that uncertainty is fitting. Quantum mechanics is not merely a collection of equations. It is also a confrontation with the limits of human intuition. The microscopic world refuses to fit neatly into ordinary categories because those categories were never designed for it in the first place. Our brains evolved to navigate forests and weather patterns, not probability clouds and quantum states. Still, There is something strangely beautiful about the image quantum physics offers. Beneath the solid appearance of reality lies a softer layer of existence, one built not from rigid certainty, but from shimmering possibilities continuously unfolding into experience, like fog slowly condensing into droplets, like a song resolving into a final note, like countless potential futures quietly narrowing into the single moment you happen to inhabit right now. And as physicists continued exploring these strange probability waves, another unsettling realization slowly emerged from the mathematics. Perhaps uncertainty itself was not merely a limitation of human knowledge. Perhaps uncertainty was woven directly into the fabric of nature. As quantum physics continued unfolding through the 1920s, physicists slowly began realizing something deeply unsettling. The strange behavior of particles was not simply a temporary problem waiting to be solved with better instruments or more careful experiments. The uncertainty reaching through the microscopic world seemed far more fundamental than that. Nature itself appeared unwilling to become perfectly definite. One of the clearest expressions of this realization came from a young German physicist named Werner Heisenberg. Heisenberg was trying to understand something that, at first glance, sounds perfectly reasonable. If particles like electrons truly exist, why can we not simply measure everything about them precisely? Why can we not know both where a particle is and exactly how fast it is moving? Classically, there seemed no reason this should be impossible. After all, if you watch a bird crossing the evening sky, you can estimate both its position and speed at the same time. If you track a train moving along rails, you can measure where it is and how quickly it travels. Everyday life trains us to believe the universe always possesses definite properties whether we measure them or not. But quantum physics kept resisting that assumption. The more carefully physicists tried to pin down a particle's exact position, the less certain its momentum became. And the more precisely they measured momentum, the fuzzier the particle's location grew. This became known as the uncertainty principle, and despite the name, it does not merely describe human ignorance. It is not saying, we simply lack good enough instruments. It is saying something stranger. At microscopic scales, nature itself may not allow perfect simultaneous certainty. This idea is often misunderstood, partly because the word uncertainty sounds temporary, almost fixable, like uncertainty before tomorrow's weather forecast or uncertainty about the outcome of a football match. But quantum uncertainty is different. It appears woven directly into reality itself. Imagine trying to photograph a hummingbird at night. If the camera shutter stays open longer, you gather more information about where the bird is, but its wings blur into motion. If you use an extremely fast shutter speed to freeze the movement, the image becomes darker and noisier. One kind of clarity comes at the expense of another. Quantum measurement behaves in a strangely similar way. To observe tiny particles, scientists must interact with them somehow. Often this involves bouncing light or other particles off the system being measured. But at quantum scales, those interactions themselves disturb the particle. The act of looking changes what is being seen, and yet Heisenberg's insight went deeper still. Even beyond measurement disturbance, the mathematics of quantum mechanics suggested that particles do not possess perfectly definite values for certain pairs of properties simultaneously. Position and momentum are not hidden exact numbers waiting quietly behind the curtain. Reality itself remains somewhat spread out, soft around the edges, like mist refusing to fully condense. This was extraordinarily difficult for many physicists to accept, because classical thinking had trained generations of scientists to imagine a deterministic universe. A universe where every event flowed inevitably from prior conditions like gears turning inside a clock. Quantum mechanics disrupted that comforting picture. Suddenly, prediction itself became probabilistic, Instead of forecasting exact outcomes with certainty, physicists could only calculate likelihoods, patterns, statistical tendencies, not because the theory was incomplete, but because probability appeared fundamental. And strangely enough, uncertainty turned out to be essential for existence itself. Consider the atom. Classically, electrons orbiting a nucleus should lose energy over time and spiral inward, collapsing into the center like planets falling into a star. Matter itself should become unstable, but that does not happen. The uncertainty principle prevents electrons from becoming confined too precisely. Their motion retains a kind of irreducible fuzziness that stabilizes atoms and allows chemistry to exist at all. In a very real sense, your body exists because perfect certainty does not. The atoms in your skin, your lungs, your heartbeat, all rely upon the quiet quantum uncertainty woven into the microscopic world. There is something strangely comforting about that. The universe is not held together despite uncertainty. It is held together through it. And perhaps this is one reason quantum physics feels so philosophically powerful. It challenges the ancient human instinct that reality must always be rigid, fixed, and fully knowable beneath the surface. Instead, nature behaves more like drifting weather patterns than clockwork machinery. Not chaos exactly, but fluidity. A structured kind of openness. Imagine standing beside the ocean just before sunrise. The horizon is visible, but soft. Waves emerge gradually from darkness. Shapes remain half-defined in the pale morning light. The scene is real, undeniably real. Yet not every detail is sharp and settled all at once. Quantum reality seems to possess a similar quality. Not unreal, not imaginary, simply less definite than human intuition expects. And the deeper physicists explored this uncertainty, the more the microscopic world began resembling a realm of overlapping possibilities rather than solid hidden certainties waiting to be uncovered. Even Einstein struggled deeply with this shift. He believed nature must ultimately possess deeper deterministic laws hidden beneath quantum probabilities. He resisted the idea that chance played a fundamental role in the structure of reality. But experiment after experiment continued favouring quantum predictions. The universe appeared stubbornly probabilistic, and perhaps the most humbling part of all this is what it reveals about human understanding itself. Our minds evolved to survive at human scales. We instinctively think in terms of solid objects, clear positions, stable identities. Yet beneath those familiar appearances lies a deeper layer of reality that does not obey those intuitive categories cleanly. Particles blur, possibilities overlap, certainty softens, and still, the universe works, stars burn, atoms hold together, galaxies drift through darkness. Life emerges from microscopic uncertainty with astonishing elegance. It is almost as though reality itself is less like stone and more like music, structured, predictable in some ways, but never fully pinned down into a single unmoving form. And somewhere within that strange quantum music, another even stranger idea was quietly waiting to emerge. The possibility that particles might exist in multiple states at once, until the moment reality finally settles into one. By now, the old image of reality as a perfectly solid machine has begun to fade considerably. Light behaves both like waves and particles. Electrons exist as probability clouds rather than tiny orbiting spheres. Uncertainty is not merely a flaw in measurement, but something built into the structure of nature itself. And still, quantum physics was only becoming stranger. Because hidden inside the mathematics of the wave function was an implication so unsettling that even the physicists who discovered it struggled to accept it emotionally. A quantum system, according to the equations, can exist in multiple possible states at the same time, not metaphorically, not because we lack information, but genuinely, until interaction or measurement forces a definite outcome. This idea is known as superposition, and although the word sounds technical, the underlying concept can be approached gently. Imagine spinning a coin on a wooden table. While spinning rapidly, the coin is not clearly heads or tails. Its state remains unresolved in a practical sense. Only when the spinning stops does one outcome settle into place. Now, quantum superposition is not exactly the same thing. A spinning coin is still physically one side or the other at every instant, even if your eyes cannot easily distinguish it. But the image helps capture the feeling of suspended certainty, a state that has not fully resolved. Quantum systems behave in ways that feel strangely similar, except the unresolved nature appears fundamental rather than merely hidden. An electron's spin can exist in a blend of possible states before measurement. A photon can travel along multiple paths simultaneously within the mathematics of the wave function. Reality itself appears capable of holding overlapping possibilities together without immediately choosing between them. And naturally, this raised uncomfortable questions. If microscopic particles can exist in superpositions, what about larger objects? Could a cat? This was the provocative thought experiment proposed by Erwin Schrödinger in 1935. Ironically, Schrödinger himself did not invent the scenario because he believed cats truly existed in bizarre quantum limbo. Quite the opposite. He designed the experiment to demonstrate how absurd quantum mechanics seemed when extended into ordinary life. The setup is famous now. Imagine a sealed box. Inside the box sits a cat beside a tiny radioactive atom, a detector, and a mechanism connected to a vial of poison. If the atom decays, the detector activates, the vial breaks, and the poison is released. If the atom does not decay, the cat remains alive. According to quantum mechanics, before observation, the radioactive atom exists in a superposition of decayed and not decayed states. And if the entire system follows quantum rules consistently, then the cat itself becomes entangled with those possibilities, alive and dead at the same time, at least mathematically. Even today, this thought experiment retains its unsettling power because it exposes the strange tension between the microscopic quantum world and the stable classical world we experience daily. After all, you do not encounter cats shimmering ambiguously between life and death in your kitchen. Coffee mugs do not exist in multiple locations simultaneously. Chairs remain where you left them. The everyday world appears wonderfully solid and definite. So where does the transition occur? At what point does quantum possibility harden into classical certainty? This became one of the deepest questions in modern physics. And perhaps what makes Schrödinger's cat so emotionally memorable is not the cat itself, but the uncomfortable feeling hiding underneath the story. The possibility that reality may not be fully settled beneath the surface, that beneath ordinary appearances the world remains softer, more fluid, and more unresolved than human intuition expects. Imagine walking through thick morning fog before sunrise. Faraway shapes overlap indistinctly. Trees blend with shadows. The landscape has not yet fully clarified itself in the pale light. Then, gradually, as brightness increases, boundaries sharpen. Possibilities narrow into definite forms. Superposition carries a strangely similar emotional texture. Before measurement, a quantum system behaves almost like overlapping futures existing together within a cloud of possibility. Measurement seems to force one path into focus, while the others fade from observation. And importantly, physicists do not all agree on what this truly means. Some interpretations suggest reality genuinely exists in multiple simultaneous states until collapse occurs. Others propose that all possible outcomes continue existing in separate branching universes. Still others argue the wave function merely describes information rather than physical reality itself. Quantum mechanics predicts experimental outcomes with extraordinary precision, but the deeper meaning beneath the mathematics remains profoundly debated, which, in a way, makes the field feel almost human. Even with all our equations, detectors, and particle accelerators, we remain creatures trying to interpret mysteries larger than our instincts evolved to handle. And perhaps that is part of why superposition feels so difficult emotionally. Human beings crave definiteness. We like clear identities, clear outcomes, stable categories. We prefer the comfort of this or that, alive or dead, here or there, past or future. Quantum physics quietly whispers that nature may not always obey those sharp boundaries. Instead, reality sometimes behaves like overlapping music drifting through walls, different notes existing together before the melody finally resolves. And remarkably, this strange principle is not merely philosophical. Modern quantum computing depends directly on superposition. Quantum bits, often called qubits, can represent combinations of states simultaneously, rather than existing strictly as simple binary choices. This allows certain computations to explore many possibilities at once, in ways classical computers cannot easily imitate. The very weirdness that once disturbed physicists is now becoming a technological resource, which is one of the recurring patterns in science. Again and again, nature first appears impossible, then slowly becomes understandable enough to reshape civilization itself. Still, beneath all the mathematics and engineering, superposition leaves us with an unsettling image. Perhaps reality is not fully written in advance. Perhaps the universe itself contains layers of unresolved possibility, continuously narrowing into experience moment by moment. Like mist becoming rain, like music resolving into harmony, like countless invisible paths quietly collapsing into the single life you happen to remember as your own. And as physicists continued wrestling with superposition, another realization slowly emerged from the quantum world. Maybe the reason ordinary reality appears stable and classical is not because quantum behavior disappears, but because the world around us constantly interacts with itself, smoothing away the visible traces of quantum possibility. After wandering through the strange terrain of superposition, where particles exist among overlapping possibilities, and Schrödinger's unfortunate cat lingers uneasily between outcomes, a natural question begins to rise. If quantum mechanics truly governs the foundations of reality, why does the world around you feel so stable? Why does your coffee mug remain firmly on the table instead of dissolving into a blur of possibilities? Why do mountains stay mountains? Why do cats, thankfully, behave like ordinary cats instead of shimmering probability clouds? Somewhere between the microscopic quantum world and the familiar human world, something changes, or at least, something appears to change. For many years, this transition remained deeply mysterious. Quantum equations described tiny systems beautifully, but they did not clearly explain how the definite world of everyday experience emerged from underlying uncertainty. Then physicists began developing an idea known as decoherence, and although the name sounds technical, the basic intuition behind it can be understood quite gently. Imagine a still pond at dawn. Its surface is smooth enough to reflect the sky almost perfectly. Tiny ripples remain delicate and coherent, spreading outward in elegant overlapping patterns. But now imagine heavy rain beginning to fall across the pond. Countless impacts disturb the surface simultaneously. The original ripples become scrambled and lost inside larger chaos. Their information spreads outward into the surrounding water. Something similar appears to happen in quantum systems. When a particle remains isolated, its delicate wave-like possibilities can stay coherent. Different potential states overlap and interfere with one another like soft ripples crossing a quiet lake. But once the system begins interacting strongly with its environment, with nearby particles, photons, vibrations, thermal energy, surrounding matter, those delicate quantum relationships begin dispersing outward. The quantum system becomes entangled with the world around it, and gradually the visible effects of superposition fade from view. This process is decoherence. Importantly, decoherence does not necessarily mean the wave function literally vanishes, nor does it fully solve every mystery surrounding measurement and collapse. Instead, it explains why quantum weirdness becomes extraordinarily difficult to observe in large systems. The environment itself continuously monitors the system through endless interactions. Reality becomes noisy. Imagine trying to hear a whisper in a crowded train station. In a quiet room, the whisper remains clear and distinct, but surrounded by hundreds of conversations, footsteps, announcements, and moving bodies, the signal becomes buried beneath interaction and interference. Quantum coherence behaves similarly. Microscopic particles can preserve delicate superpositions for short periods under carefully controlled conditions, but large objects constantly interact with trillions upon trillions of surrounding particles. Air molecules collide with them, light bounces off them, heat vibrates through them. The world is endlessly touching itself, and because of that, coherent quantum behavior becomes hidden beneath layers of environmental interaction. One helpful way to picture this is through the image of a frozen lake. Beneath the ice lies moving water, fluid, shifting, dynamic. But the surface appears solid and stable. You can walk across it confidently without directly experiencing the restless motion underneath. Decoherence is somewhat like that freezing process. The deeper quantum world never fully disappears. Instead, interaction with the environment creates the sturdy classical reality we experience daily. The fluid possibilities underneath become masked by stable, large-scale patterns, and the more connected an object is to its surroundings, the stronger this classical appearance becomes. A single isolated electron in a laboratory can preserve quantum coherence briefly under controlled conditions. A cat, meanwhile, interacts continuously with air, heat, light, sound, gravity, bacteria, dust, and countless other systems every moment. Its quantum possibilities decohere almost instantly, which is why the world feels definite, not because the quantum realm ceases to exist, but because coherence becomes diluted into the environment too rapidly for us to observe directly. There is something strangely beautiful about this idea. Reality may not emerge through sudden dramatic collapse alone, but through continuous interaction. A gradual settling, a soft freezing of possibility into stable experience, like fog condensing slowly into droplets, like ripples smoothing into stillness, like countless overlapping melodies resolving into a single recognizable song. And remarkably, decoherence has become essential not only for philosophy, but for technology as well. Quantum computers, for example, must constantly battle decoherence. Their quantum bits rely on fragile superpositions and entanglements. Even tiny environmental disturbances can disrupt those states, causing the quantum behavior to fade into ordinary classical outcomes. This is why quantum systems are often kept in extremely cold, isolated environments. Engineers work tirelessly to preserve coherence long enough for meaningful computation to occur. The quantum world, it turns out, is astonishingly delicate, almost shy. It reveals itself most clearly only when protected from the noisy warmth of ordinary reality. And yet, despite all this progress, decoherence still leaves important questions unanswered. It explains why superpositions become effectively invisible in large systems, but it does not fully explain why one specific outcome becomes real in any individual measurement. Why this result instead of another? Why this version of reality? The mathematics remains extraordinarily successful, but interpretation still drifts through philosophical fog. And perhaps that lingering ambiguity is part of what makes quantum physics feel so hauntingly compelling. The universe does not hand us perfect certainty. Instead, it offers patterns, probabilities, structures emerging from interaction. The classical world around you may not be separate from the quantum world beneath it. It may simply be what quantum reality looks like after endless layers of interaction smooth its edges into stability, like ocean waves viewed from high above. Up close, the water churns chaotically with foam and turbulence, but from a distance, the surface appears calm and unified. Human experience may occupy that distant scale. We live atop the frozen surface of a deeper quantum sea, rarely noticing the fluid uncertainty quietly moving underneath. And perhaps there is something comforting hidden inside that image. The stable world you know is not an illusion exactly. The chair beneath you is real. The room around you exists. The stars beyond the window continue their silent drift through darkness. But beneath that stability lies motion, possibility, a softer layer of reality continuously interacting with itself until the universe settles, moment by moment, into the experience we call ordinary life. And as physicists explored these interactions more deeply, they discovered something even stranger waiting nearby. Particles separated by enormous distances, behaving as though they remained mysteriously connected. Even after decoherence helped explain why the everyday world appears stable and classical, one deep mystery remained quietly unresolved beneath the surface. What actually causes a quantum possibility to become a definite outcome? Or perhaps more unsettling still, does anything truly collapse at all? The mathematics of quantum mechanics works with astonishing precision. Few scientific theories in history have matched experimental reality so accurately. Quantum predictions guide modern electronics, lasers, chemistry, medical imaging, and countless technologies surrounding everyday life. And yet, beneath all that success, physicists still disagree profoundly about what the equations actually mean. Not the calculations themselves, the meaning underneath them. This is one of the strangest aspects of quantum physics. Imagine building a machine that functions perfectly every time. While nobody fully agrees on what the machine is fundamentally doing, that is roughly the situation physicists find themselves in even today. And so, over the decades, different interpretations of quantum mechanics emerged. Different attempts to tell a coherent story about what reality may truly be beneath the mathematics. The oldest and most famous interpretation is known as the Copenhagen interpretation, largely associated with Niels Bohr and Werner Heisenberg. According to this view, the wave function does not necessarily describe physical reality itself in a direct way. Instead, it describes probabilities, possible outcomes that become definite when measurement occurs. Before observation, asking where a particle really is may not even be meaningful. The particle is not secretly hiding in one precise location waiting to be discovered. Instead, reality remains fundamentally unresolved until interaction produces an observable result. This interpretation is practical and mathematically successful. In many ways, it became the standard working philosophy of 20th century quantum physics. But emotionally, many people found it difficult to accept, because it leaves a strange feeling lingering in the mind. If reality only becomes definite through measurement, what exactly counts as a measurement? A detector? A photon? A conscious observer? a recording device quietly sitting in darkness. The Copenhagen interpretation works beautifully as physics, while leaving philosophy wide open, and naturally not everyone was satisfied with that uncertainty. Among the most radical alternatives is the many worlds interpretation. This idea proposes something astonishing. What if the wave function never collapses at all? What if every possible outcome actually occurs, but in separate branching realities? In this picture, measuring a particle does not force the universe to choose one result. Instead, reality itself splits into multiple versions. In one branch, the particle appears one way. In another branch, it appears differently. Each outcome continues unfolding in its own parallel history. You experience only one branch, but the others still exist. Some physicists admire the mathematical elegance of this interpretation because it removes the need for mysterious collapse entirely. The equations simply continue evolving smoothly forever. But emotionally, the idea can feel overwhelming. A constantly branching cosmos, worlds endlessly dividing like reflections inside mirrors facing one another. Every choice, every interaction, every quantum event generating new layers of reality beyond observation. There is something both beautiful and dizzying about it. Like standing beneath an infinite night sky filled not only with stars, but with endless unseen versions of existence quietly unfolding beside your own. And still, other physicists sought different answers. Some proposed what are called objective collapse theories. In these interpretations, wave function collapse is a real physical process built directly into nature itself. Superpositions remain possible for small systems, but beyond certain scales or conditions, reality spontaneously settles into definite outcomes. No observer required. Nature itself performs the collapse. These theories attempt to preserve a more concrete physical reality beneath quantum behavior, though they remain experimentally difficult to confirm. Then there are even more unusual interpretations. One modern approach, sometimes called cubism, suggests that the wave function may not describe objective reality at all. Instead, it represents an observer's knowledge, expectations, or beliefs about possible outcomes. In this view, quantum mechanics becomes less a description of the universe itself, and more a guide for updating information through experience. Reality does not necessarily change during measurement. Your knowledge changes. Some physicists find this deeply refreshing, others find it profoundly unsatisfying. After all, people tend to want physics to describe the external universe, not merely our relationship to it. And through all these interpretations, one thing becomes increasingly clear. Quantum mechanics is not merely a scientific theory. It is also a mirror held up to human understanding itself. Because beneath every interpretation lies the same quiet tension. What kind of thing is reality when nobody is looking? The unsettling truth is that modern physics does not yet provide one universally accepted answer, and perhaps that uncertainty feels uncomfortable because human beings instinctively crave finality. We want clean conclusions, solid categories, a world that resolves neatly into certainty. But quantum physics continues resisting that impulse. Again and again, the microscopic world behaves less like rigid machinery, and more like overlapping possibility waiting to settle into experience. Imagine clouds drifting across a moonlit sky. From a distance, shapes emerge briefly before dissolving again. Boundaries blur, patterns shift softly. Nothing remains perfectly fixed for very long. Quantum reality often feels emotionally similar. Not chaotic exactly, not meaningless, but fluid in ways the human mind does not naturally expect. And perhaps this is why quantum mechanics continues captivating people, far beyond physics itself. The theory touches something ancient and philosophical beneath the mathematics. It challenges the assumption that reality must always possess definite hidden structure, independent of interaction. Maybe certainty is not the default state of existence. Maybe certainty emerges gradually, locally, temporarily, from deeper layers of possibility. And maybe the universe itself is more comfortable with ambiguity than human beings are. Still, despite all these debates, experiments continue confirming quantum predictions with extraordinary reliability. Whatever interpretation eventually proves closest to truth, the strange probabilistic structure of quantum mechanics appears deeply woven into reality itself, and soon physicists would discover an even more astonishing phenomenon emerging from that structure: particles separated by enormous distances, behaving as though space itself could not fully divide them. A phenomenon so strange that Einstein himself called it spooky. As physicists continued exploring the quantum world, they slowly discovered that uncertainty and superposition were not the end of the strangeness. In some ways, they were only the beginning, because hidden inside the mathematics of quantum systems was another phenomenon so deeply unsettling that Albert Einstein himself struggled to accept it fully. A phenomenon suggesting that particles separated by enormous distances could still behave as though they shared something invisible between them. Not a signal exactly, not a physical thread stretching across space, but a connection of correlations so precise that it seemed to challenge ordinary ideas about separation itself. This phenomenon became known as quantum entanglement, and even now, more than a century later, it remains one of the most astonishing discoveries in modern science. To approach entanglement gently, it helps to begin with something familiar. Imagine placing a pair of matching gloves into separate boxes. One glove is left-handed, the other right-handed. You send one box to the far side of Earth while keeping the other nearby. The moment you open your box and see the left glove, you instantly know the distant box contains the right glove. No mystery there. The gloves possess definite properties all along. Quantum entanglement initially appears similar, but then reality quietly slips sideways into something much stranger. When two quantum particles become entangled, certain properties of the system remain linked together. Measuring one particle instantly determines the corresponding outcome for the other, even if the particles are separated by enormous distances. And unlike the glove example, the particles do not necessarily appear to possess definite hidden values beforehand in the classical sense. The correlations emerge only during measurement itself. This deeply disturbed Einstein. He worried quantum mechanics might be incomplete because entanglement seemed to imply what he famously called spooky action at a distance. The phrase was partly humorous, but also genuinely uneasy. Einstein believed reality should remain local. Objects here should not instantly influence objects far away without something travelling between them. Space, after all, appears to separate things, and yet quantum experiments kept producing entangled correlations stronger than classical physics allowed. Over time, physicists developed increasingly precise tests to explore this mystery. Among the most important were experiments inspired by physicist John Bell in the 1960s. Bell discovered a way to test whether hidden classical explanations could reproduce quantum predictions. Again and again, experiments sided with quantum mechanics. The universe appeared to reject certain forms of classical local realism, and importantly, this does not mean particles are secretly sending messages faster than light. Entanglement cannot be used like cosmic telepathy or instantaneous communication devices. No usable signal travels between the particles in a controllable way. The deeper mystery is subtler. The particles behave as though their properties were never entirely separate to begin with, as though the quantum system forms one shared structure extending across space. Imagine two dancers performing perfectly synchronized movements while standing miles apart in darkness. not because they are actively signaling one another moment by moment, but because they remain expressions of the same choreography. Entanglement feels strangely similar. The particles are not necessarily whispering information through hidden tunnels in space. Instead, quantum mechanics suggest their properties may belong to a deeper shared description that ordinary distance does not fully divide. And perhaps this is one reason entanglement feels so emotionally powerful. Human beings instinctively experience the universe as fragmented into separate objects. You here, the stars there, one person isolated from another by distance, time, and space. Entanglement quietly hints that at deeper levels of reality, separateness may not always behave the way human intuition expects. Not in a mystical sense, not as magic, but as a reminder that the microscopic foundations of existence are stranger and more interconnected than classical physics once imagined. And remarkably, entanglement is not merely theoretical. Scientists have observed it repeatedly in laboratories using photons, electrons, atoms, and other quantum systems. Entangled particles have been separated across kilometers, through fiber optic cables, across mountaintops, and even between Earth and satellites orbiting above the planet. The correlations persist, quietly, reliably, almost unnervingly. There is something hauntingly beautiful about that image. Tiny particles born together in quantum interaction, drifting far apart through space while still behaving like different expressions of the same hidden pattern. Like echoes spreading across a canyon, like matching ripples travelling outward from the same stone dropped into water. And in recent years, entanglement has become one of the foundations of emerging quantum technologies. Quantum cryptography uses entangled particles to help detect eavesdropping attempts. Quantum teleportation experiments transfer quantum states between systems using entanglement and classical information together. Future quantum networks may depend heavily upon these strange correlations. The phenomenon that once seemed philosophically absurd is gradually becoming technologically practical. And still, its deeper meaning remains debated. Some physicists interpret entanglement as evidence that reality itself is fundamentally non-local in certain ways. Others argue the mathematics simply transcends classical intuitions about separateness, without requiring mysterious faster-than-light influence. Even now, no interpretation fully dissolves the feeling of strangeness, and perhaps that lingering discomfort is valuable, because entanglement reminds us that human intuition evolved within a narrow slice of reality. Our ancestors survived by understanding rocks, trees, rivers, predators, weather, and social relationships. Nothing in human evolution prepared the brain to intuit the behavior of entangled quantum systems spread across space. The microscopic universe is under no obligation to feel emotionally familiar. Still, there is something oddly calming hidden beneath the mystery. Entanglement does not tell us that consciousness controls reality, or that minds communicate magically across the cosmos. The actual science remains more grounded and subtle than that. But it does suggest that the universe may be woven together more deeply than appearances imply, that beneath the visible separation of things lies a quieter layer of shared structure, a hidden coherence beneath ordinary distance. And as physicists continued studying these invisible quantum connections, they discovered another remarkable behavior waiting nearby. Particles confronting barriers that classical physics declared impossible to cross, and slipping through anyway, like fog drifting softly beneath a closed door. By now, the quantum world has begun to feel less like a collection of tiny mechanical objects, and more like a shifting landscape of probabilities, connections, and possibilities. Particles spread like waves. Reality softens before measurement. Entangled systems remain mysteriously linked across distance. And still, nature had another surprise waiting quietly beneath the surface. a phenomenon so strange that, from the perspective of classical physics, it should not happen at all. Quantum tunneling. To understand why tunneling feels so surprising, imagine rolling a ball toward a hill. If the ball lacks enough energy, it simply rolls partway upward before falling back down. Common sense tells us this immediately. To cross the hill, the ball must possess sufficient energy to climb over it. Classical physics behaves exactly this way. Barriers remain barriers, walls remain walls, limits remain firm. But quantum particles do not behave like tiny solid marbles moving along definite paths. They behave more like waves of probability spread through space. And waves, unlike rigid objects, can sometimes leak beyond boundaries. Imagine fog drifting beneath a doorway on a cold morning. The door appears closed, yet faint wisps still seep through the cracks. Or imagine hearing music from another apartment late at night. The walls remain solid, but the vibrations quietly pass through them anyway. Quantum tunneling feels strangely similar. When a quantum particle encounters an energy barrier, classical physics predicts it should stop if it lacks sufficient energy to cross. Yet because the particle behaves as a probability wave rather than a perfectly localized object, part of its wave function can extend through the barrier, and occasionally, a measurable probability appears on the other side. The particle tunnels through, not by smashing through the wall, not by violating physics, but because quantum reality is governed by probabilities rather than rigid classical certainties. At microscopic scales, the universe behaves less like locked doors and more like overlapping possibilities. This idea first seemed almost unbelievable to physicists, yet experiment after experiment confirmed it. Particles really could appear beyond barriers they classically should never cross. And remarkably, tunneling is not some rare laboratory curiosity hidden inside advanced physics departments. It plays an essential role in the existence of stars themselves, including the Sun. Deep within the Sun's core, atomic nuclei move under extraordinary pressure and temperature. Yet even there, according to classical calculations alone, many nuclei should still repel one another too strongly to fuse together easily. Their positive electric charges create a barrier resisting close contact. And yet, fusion happens constantly. Hydrogen nuclei merge into helium, energy pours outward. Sunlight fills the solar system. Why? Because quantum tunneling allows some particles to slip through the barrier despite lacking the classical energy to fully overcome it. The sun shines because probability leaks through walls. There is something almost poetic about that. Every warm sunrise, every leaf illuminated in morning light, every quiet afternoon beneath drifting clouds, all ultimately depend upon tiny quantum events unfolding deep inside a star. Without tunneling, stellar fusion would slow dramatically. The cosmos itself would look profoundly different. Many stars might never shine steadily enough for planets and life to emerge around them. Quantum uncertainty once again proves essential to existence, and tunneling appears elsewhere too. Radioactive decay depends partly upon tunneling processes within unstable atomic nuclei. Certain particles trapped inside nuclei eventually tunnel outward, escaping despite barriers that classically should confine them. Even modern technology quietly relies on tunneling effects. Scanning tunneling microscopes, for example, use delicate quantum tunneling currents to map surfaces at astonishingly tiny scales, allowing scientists to visualize individual atoms indirectly. The device functions because electrons can tunnel across microscopic gaps between surfaces. The strange softness of quantum reality becomes measurable engineering, and still, beneath all these practical applications, tunneling retains a dreamlike quality. It challenges one of the deepest assumptions inherited from classical intuition, that objects possess rigid boundaries and definite paths. Quantum particles do not experience the universe quite the way macroscopic objects do. A human being cannot tunnel through a mountain because decoherence overwhelms large systems almost instantly. The stable classical world emerges too strongly at human scales, but microscopic particles retain their wave-like probability behavior long enough for tunneling to occur measurably. The deeper quantum world never fully disappears beneath everyday reality. It simply becomes hidden beneath stability. Imagine ocean waves reaching a rocky shoreline at night. Most waves crash and fall back, yet small streams of water occasionally seep quietly through cracks in the stone, appearing unexpectedly on the other side. Not because the rocks cease existing, but because fluid systems interact differently with barriers than solid objects do. Quantum particles behave with similar fluidity, not liquid exactly, not ghost-like, but probabilistic in ways ordinary human intuition struggles to visualize cleanly, and perhaps that difficulty itself is important. Quantum physics repeatedly reminds us that the universe is not obligated to organize itself according to the categories human beings evolved to understand easily. The microscopic world behaves according to structures deeper than everyday common sense. Still, tunneling carries an oddly comforting emotional texture. It suggests that boundaries in nature are sometimes softer than they appear, not meaningless, not absent, but permeable under the right conditions, probability quietly reaching beyond classical limits. And beyond tunneling itself, physicists soon discovered something even stranger waiting underneath all particles and forces entirely. The possibility that matter is not made primarily of isolated objects at all, but of invisible fields filling the universe continuously, even in the emptiness of space itself. Because in the quantum world, even emptiness refuses to remain truly empty for very long. By this point in our journey, the universe has become far stranger than the old clockwork picture once imagined. Particles spread through probabilities, matter tunnels through barriers, distant systems remain mysteriously entangled. Even certainty itself appears softer and more fluid than human intuition prefers. And now, quantum physics invites us toward another unsettling possibility. That empty space may not truly be empty. At first glance, emptiness feels simple. A dark room after the lights are switched off, the silent gap between stars, the vast blackness stretching between galaxies. Human beings naturally imagine empty space as absence, a kind of cosmic nothingness waiting quietly behind matter and light. But quantum physics began revealing something very different. Even in a perfect vacuum, where all matter has been removed as completely as possible, subtle activity still remains. The vacuum itself seems restless, not violently restless, not chaotic in the ordinary sense, more like a faint trembling hidden beneath apparent stillness. Imagine entering a quiet forest before sunrise. At first, everything seems motionless. The air is calm, shadows linger softly between trees. Yet as your attention settles, tiny movements slowly emerge, leaves shifting gently, insects stirring beneath bark, distant wind brushing branches almost invisibly. Stillness, you realize, was never truly empty. The quantum vacuum appears strangely similar. According to quantum field theory, space is not simply a blank container in which particles float around like dust drifting through air. Instead, fields permeate the universe continuously. Even where no particles are visibly present, these fields remain. And fields do not rest perfectly still. Tiny fluctuations ripple through them constantly. The vacuum hums quietly beneath reality. Now, popular descriptions often say that virtual particles pop in and out of existence. While that image captures part of the intuition, the deeper picture is more subtle than tiny invisible fireworks randomly appearing in empty space. What physicists actually observe are measurable effects arising from the restless behavior of quantum fields themselves. The vacuum possesses structure, activity, instability at microscopic scales. Space is not a perfectly silent void. It is more like a dark ocean whose surface never becomes completely motionless. One of the most fascinating demonstrations of this idea is known as the Casimir effect. The setup sounds almost impossibly delicate. If two extremely thin metal plates are placed extraordinarily close together in a vacuum, quantum fluctuations between the plates become slightly restricted compared to the fluctuations outside them. This creates a tiny measurable pressure pushing the plates together. In other words, empty space itself produces physical effects. Not metaphorically, literally measurable ones. There is something deeply strange about that realization. The vacuum is not passive nothingness. It behaves more like a hidden background sea of fluctuating possibility beneath visible matter. And as physicists explored these fluctuations more deeply, another astonishing implication slowly emerged. Perhaps particles themselves are not permanent little objects drifting through emptiness, but temporary excitations arising from underlying fields, like ripples appearing briefly on water, which means the distinction between something and nothing becomes less clear than human intuition expects. Even apparent emptiness contains activity waiting beneath the surface. This strange, restless quality of the vacuum may also connect to some of the largest mysteries in cosmology. Modern observations suggest the expansion of the universe is accelerating, driven by what scientists call dark energy. Although its true nature remains unknown, some physicists have explored whether vacuum energy itself might play a role. The emptiness of space may influence the fate of the cosmos. An extraordinary thought. The vast silent regions between galaxies, seemingly barren and inactive, may contain subtle energy woven into the structure of reality itself. And quantum fluctuations may not merely influence the modern universe, they may have shaped the early cosmos as well. Some cosmological models suggest tiny quantum fluctuations during the universe's earliest moments became stretched across enormous scales during cosmic inflation. Over immense stretches of time, gravity amplified those tiny ripples into the large-scale structure of galaxies and cosmic filaments we see today. The stars themselves may trace patterns born from microscopic uncertainty, the visible universe emerging from faint fluctuations in the quantum vacuum. There is something hauntingly beautiful about that image. Galaxies as frozen echoes of ancient quantum ripples, light years of structure arising from tiny restless variations in fields billions of years ago. And still, the quantum vacuum becomes stranger. In the 1970s, physicist Stephen Hawking discovered that black holes may not be entirely black after all. Through subtle quantum effects near the event horizon, black holes can slowly emit what is now called Hawking radiation. The mechanism is complex and still interpreted carefully by physicists, but the deeper emotional implication is astonishing. Even the darkest regions of space are touched by quantum activity. The vacuum itself never fully sleeps. Not beside black holes, not between galaxies, not even inside apparent emptiness. And perhaps this is one of the most quietly transformative ideas quantum physics offers. Human intuition tends to divide reality sharply into categories: something and nothing, matter and emptiness, presence and absence. But quantum theory keeps dissolving those hard boundaries. The vacuum is not perfectly empty. Particles are not perfectly solid. Certainty is not perfectly fixed. Reality behaves less like rigid architecture and more like patterns continuously rising and fading within deeper invisible fields. like waves briefly appearing on a dark ocean at night. And emotionally, there is something oddly peaceful about that vision. The universe no longer feels built from isolated hard objects scattered through dead emptiness. Instead, existence resembles an interconnected sea of fluctuating structure, dynamic even in silence, active even in darkness. The stillness beneath reality is not lifeless. It hums softly beneath everything. And as physicists gradually followed these invisible quantum fields deeper, they began arriving at an even more radical idea. Perhaps particles themselves are not the true foundation of reality at all. Perhaps the fields come first. As the idea of the quantum vacuum settles softly into place, another realization begins to emerge from the darkness behind it. Perhaps particles are not the deepest layer of reality after all. For centuries, human beings imagined matter as being built from smaller and smaller objects. Stones broken into grains, grains broken into molecules, molecules into atoms, atoms into electrons and nuclei, always smaller pieces hidden inside larger ones, like nested boxes stretching downward without end. But modern quantum physics gradually led scientists toward a different picture. Not a universe made primarily of tiny objects moving through emptiness, but a universe filled with invisible fields, continuous, everywhere, even in regions we call empty space, and within those fields, particles appear almost like temporary patterns rising from a deeper sea. This idea forms the foundation of what physicists call quantum field theory. The mathematics behind it can become extraordinarily complex, but the underlying intuition can be approached gently. Imagine standing beside the ocean at night. The surface of the water appears alive with waves. Some waves rise higher than others, some dissolve quickly, others travel long distances before fading into darkness. Yet none of the waves exist independently from the ocean itself. The wave is not separate from the water, it is a behavior of the water. Quantum fields work in a strangely similar way. According to modern physics, what we call an electron is not primarily a tiny permanent object drifting through space like a microscopic pebble. Instead, there exists an electron field extending throughout the universe. What we observe as an electron is a localized excitation within that field, a ripple, a vibration, a temporary pattern emerging from something deeper and continuous. The same idea applies to photons, the particles of light. There is a photon field. Disturbances within that field appear to us as photons. Quarks arise from quark fields. Other particles emerge from their own corresponding fields. The field comes first. The particle is what the field does. This represents one of the most profound shifts in modern science because it transforms our image of reality itself. The universe no longer resembles empty space sprinkled with isolated objects. Instead, it becomes more like an immense interconnected ocean of invisible activity. Fields everywhere, ripples moving through them, patterns briefly stabilizing into what we perceive as matter. Imagine placing your hand near a speaker while music plays softly through a room. You cannot directly see the sound waves moving through the air, yet their presence becomes undeniable through vibration and resonance. Different notes produce different patterns. Different frequencies create different textures of motion. Quantum fields behave somewhat similarly. The fields themselves remain invisible, but their excitations become observable as particles with specific properties: mass, charge, spin, energy. Reality begins to resemble music played upon invisible instruments, and perhaps this is one reason quantum field theory feels emotionally different from classical physics. The old mechanical universe imagined solid objects interacting externally like gears inside a clock, but quantum fields suggest something softer and more unified. Matter is no longer fundamentally separate from space. Particles are no longer independent little things. Everything emerges from deeper underlying fields woven continuously throughout the cosmos. Even you. The atoms inside your body are composed of stable quantum excitations, persisting within fields that stretch far beyond Earth itself. The electrons inside your cells are not isolated objects belonging uniquely to you. They are local expressions of a universal electron field extending across the entire observable universe. There is something strangely humbling about that realization. The boundaries between object and environment begin to soften. You're not standing apart from reality observing it from outside. You're one temporary pattern arising within it, like a whirlpool forming briefly within a river, distinct for a time, yet never fully separate from the larger flow surrounding it. And among all these fields, one became especially important in explaining a profound mystery: mass. Why do some particles possess mass while others do not? Why can light travel endlessly through space while other particles move more sluggishly through the universe? Physicists eventually discovered evidence for another field permeating reality: the Higgs field. Rather than imagining the Higgs field as a substance objects crash into mechanically, it may help to picture it more gently. Imagine people walking through a crowded room at a gathering. Some move easily and quickly through the crowd. Others become slowed because interactions form around them continuously. The more strongly something interacts with the surrounding environment, the harder it becomes to move freely. The Higgs field behaves somewhat similarly. Particles interacting strongly with the Higgs field acquire greater mass. Particles interacting weakly move more freely. Mass emerges through relationship, not isolation. And again, the universe feels less like rigid machinery and more like a web of interactions continuously shaping one another. Even empty space itself contains these fields. The vacuum is never truly blank. It hums quietly beneath existence with invisible structure and restless possibility. And remarkably, quantum field theory has proven astonishingly successful. Its predictions align with experiments to extraordinary precision. Modern particle physics, chemistry, and much of modern cosmology rely upon this framework. And yet, despite its success, the emotional implications remain quietly profound. Reality appears less solid than human intuition once imagined. Matter becomes vibration. Particles become temporary excitations. Space becomes active. The universe transforms into something fluid, dynamic, and deeply interconnected beneath appearances, like waves moving across an endless sea beneath moonlight. Distinct for a moment, then fading back into the larger field from which they emerged. And as physicists continued mapping these invisible quantum fields, they gradually assembled an intricate portrait of the fundamental particles and interactions shaping ordinary matter itself. A structure elegant enough to explain much of the visible universe, while still leaving some of the deepest mysteries unresolved. Once physicists began seeing reality through the lens of quantum fields, the universe slowly transformed from a collection of isolated objects into something far more interconnected. Fields stretched everywhere. Particles emerged as ripples within them. Mass arose through interaction. And naturally, scientists began asking another enormous question. If all matter and forces emerge from underlying quantum fields, what are the fundamental patterns shaping the visible universe? Over many decades, physicists gradually assembled an extraordinary framework known as the Standard Model of Particle Physics. The name itself sounds oddly modest for something so ambitious, because the Standard Model is not simply a list of particles. It is one of humanity's deepest attempts to describe the hidden architecture beneath ordinary reality. A map of the microscopic patterns giving rise to stars, planets, oceans, trees, and living bodies. And despite its intimidating reputation, the emotional heart of the Standard Model is surprisingly simple. Reality appears to be built from a small number of fundamental fields interacting through elegant rules, not unlike music arising from a limited number of notes arranged into endless combinations. At the foundation of ordinary matter are particles known as quarks and leptons. Now, rather than memorizing categories or names, it helps to think of them more gently. Quarks combine together to form larger structures such as protons and neutrons, which in turn form atomic nuclei. Leptons include particles like electrons, the tiny quantum excitations surrounding atomic nuclei and helping create chemistry itself. Nearly everything you touch is built from these interacting patterns. The wood of a table, the calcium in your bones, the oxygen moving through your lungs, the iron drifting through your blood. All of it emerges from a surprisingly small set of underlying ingredients woven together through quantum fields. There is something strangely beautiful about that simplicity. An entire universe of mountains, storms, forests, oceans and galaxies emerging from a relatively compact collection of microscopic relationships, like endless symphonies composed from the same handful of musical notes. But particles alone are not enough. The Standard Model also describes forces, the interactions allowing matter to influence other matter, and again, quantum physics reshapes the old classical picture. In everyday intuition, forces often feel invisible but straightforward. A magnet pulls on metal, gravity draws objects downward, light radiates outward from the sun. But within quantum field theory, interactions themselves become exchanges between fields. Particles communicate through other particles, not consciously of course, but through tiny quantum interactions propagating across fields. Photons, for example, are associated with the electromagnetic interaction. They help mediate the forces responsible for light, chemistry, electricity, and much of ordinary matter's behaviour. Without electromagnetism, atoms could not form stable structures. Chemistry would disappear. Life itself would become impossible. Other interactions govern radioactive decay and the binding of atomic nuclei together deep inside stars. Reality becomes less like separate objects pushing one another mechanically, and more like an ongoing conversation unfolding across invisible fields. A dance of relationships, a web of exchanges. And among all the discoveries within the Standard Model, few captured public imagination more than the Higgs boson. For decades, physicists suspected the existence of the Higgs field because their equations suggested something in the universe was giving particles mass. Yet the field itself remained elusive. Then, in 2012, scientists working at the Large Hadron Collider near Geneva announced evidence for the Higgs boson, an excitation of the Higgs field. The discovery became global news. Sometimes people casually call the Higgs boson the God particle, though many physicists dislike the phrase because it sounded mystical and misleading. The actual science is subtler and more elegant than sensational headlines suggested. The Higgs field is not magic. It is part of the quiet structure underlying reality. And emotionally, the idea is rather extraordinary. Particles gain mass not because mass is some permanent internal essence, but because of interaction with a field permeating all of space. The universe shapes matter relationally. Again and again, quantum physics gently dissolves the image of isolated, independent objects. Everything interacts. Everything emerges through relationship. And yet, despite the immense success of the Standard Model, physicists know it remains incomplete. Remarkably successful, but incomplete. The theory describes 3 of the 4 known fundamental interactions extraordinarily well. It accurately predicts countless experimental outcomes. Modern particle accelerators repeatedly confirm its calculations with astonishing precision. But gravity still resists full integration into the quantum framework. Dark matter remains unexplained, dark energy remains mysterious, and the Standard Model contains numerous values and patterns that appear almost strangely arbitrary, as though deeper layers of structure may still wait undiscovered beneath it. It is a map of reality, but perhaps not the final map, and there is something comforting in that incompleteness. Science is often imagined as a process of replacing mystery with certainty. But quantum physics repeatedly teaches a gentler lesson. Each discovery reveals structure, while simultaneously uncovering deeper questions waiting underneath. The universe becomes more understandable and more mysterious at the same time, like climbing a mountain only to discover larger mountain ranges stretching beyond the horizon. Still, the Standard Model remains one of humanity's most astonishing intellectual achievements. Through mathematics, experimentation, and decades of collaborative effort, human beings learn to glimpse patterns hidden unimaginably far beneath ordinary experience. Patterns shaping atoms, stars, galaxies, life itself. And quietly, beneath all those patterns, another idea was beginning to emerge from modern physics. Perhaps information, not matter, may ultimately prove the deepest layer of reality. Because in the strange world of quantum mechanics, even black holes, those vast dark regions where gravity overwhelms light itself, seem unable to fully erase the patterns written into the universe. As quantum physics continued unfolding through the 20th century, scientists slowly began realizing that particles and fields might not be the deepest layer of reality after all. Beneath matter, beneath forces, perhaps even beneath space itself, another concept kept appearing quietly in the equations: information. Not information in the everyday sense of text messages, books, or computer files, but something more fundamental: the arrangement of physical states, the patterns describing how a system is organized, the invisible structure distinguishing one possible reality from another. And strangely enough, some of the deepest questions about information emerged from the darkest objects in the universe: black holes. For a long time, black holes seemed relatively simple in a certain brutal way. Gravity becomes so intense that beyond a boundary called the event horizon, nothing escapes. Not stars, not planets, not even light itself. A cosmic one-way door. Anything crossing the horizon appears lost forever to the outside universe. And at first glance, this creates a troubling problem. Imagine burning a book. The pages blacken, the paper curls into ash, smoke drifts upward into the air. At first it seems the information inside the book has been destroyed completely, but according to ordinary quantum physics, information is not supposed to vanish absolutely. In principle, if you could track every particle and interaction perfectly, the information describing the original book would still exist within the transform system, scattered into heat, smoke, ash, and surrounding air. Hopelessly scrambled, perhaps, but not erased. Nature appears to preserve information, and then black holes entered the story. What happens if you throw the book into a black hole instead? Not merely the physical object, but the information describing it. Does the universe truly lose that information forever? For decades, this became one of the most profound puzzles in theoretical physics, because quantum mechanics strongly suggests information should be preserved, while black holes appeared capable of destroying it permanently. Two enormously successful pillars of modern physics seem to conflict with one another. And the paradox deepened further in the 1970s when Stephen Hawking made a remarkable discovery. Black holes, according to Hawking's calculations, are not entirely black. Through subtle quantum effects near the event horizon, black holes slowly emit faint thermal radiation. Over unimaginable stretches of time, they can gradually lose mass and eventually evaporate. This became known as Hawking radiation, and emotionally, It is one of the strangest ideas in modern science. Even the darkest structures in the cosmos are not eternal. Black holes slowly fade, like embers cooling in cosmic darkness. But Hawking radiation created another terrifying implication. If a black hole eventually disappears completely, what happens to the information contained within everything it swallowed? Does the information vanish permanently from the universe? If so, quantum theory itself may require revision. If not, where is the information hiding? This became known as the black hole information paradox, and remarkably, physicists still debate aspects of it even today. Over time, many researchers came to suspect that information is not truly destroyed by black holes. Instead, it may become encoded in extraordinarily subtle ways within Hawking radiation itself, or within the structure of space-time surrounding the event horizon. The universe may hide information without erasing it. There is something hauntingly beautiful about that possibility. Imagine throwing countless stories into darkness. Books, memories, planets, stars, and discovering that reality still preserves faint traces of their structure somewhere beneath the surface, like footprints buried beneath snow, like echoes lingering after music fades. And gradually, these ideas began reshaping the way some physicists think about reality altogether. Perhaps information is more fundamental than matter itself. After all, particles can transform into energy. Fields fluctuate continuously. Atoms form and dissolve inside stars. Even black holes may evaporate over immense spans of time. But patterns, relationships, information, those may persist more deeply. Some theoretical ideas even suggest space-time itself could emerge from deeper informational structures beneath ordinary reality. In certain interpretations of modern physics, the universe begins resembling not merely a collection of objects, but a vast evolving network of relationships and encoded possibilities. Reality as process rather than static substance. The cosmos remembering itself through structure. And although these ideas remain speculative in many ways, they reveal how profoundly quantum mechanics has transformed human thought. Physics no longer studies merely things. Increasingly, it studies patterns, interactions, probabilities, and information woven through invisible fields. The universe becomes less material in the old classical sense, more relational, more dynamic, more subtle, and perhaps there is something emotionally familiar hidden inside that shift. Human life itself is deeply tied to information. A person is not merely matter. The atoms in your body change continuously throughout your lifetime. Cells die and regenerate. Air moves through your lungs. Food becomes tissue. Water leaves and returns, and yet your patterns persist. Your memories, your voice, your habits, your sense of self moving through time. The continuity of existence seems tied less to static material and more to organized information unfolding through changing matter. Quantum physics quietly hints that the universe itself may behave similarly. Patterns enduring through transformation, structure surviving beneath change. And still, the information paradox remains unresolved enough to humble physicists profoundly. Despite decades of brilliant work, no complete unification of quantum mechanics and gravity yet exists. The equations guiding the microscopic world still resist full reconciliation with the equations describing space-time and cosmic gravity. Two extraordinarily successful maps of reality, without a fully completed bridge between them, and perhaps that incompleteness is appropriate. Because the deeper physics explores reality, the more the universe resembles something fluid and layered rather than final and absolute. Matter dissolves into fields. Fields fluctuate through probabilities. Information hides within structure. and certainty itself softens into patterns emerging from deeper unknowns, like stars reflected on dark water, beautiful, real, yet never fully grasped in stillness. And while physicists searched for answers within black holes and quantum information, another realization slowly emerged from the living world itself. Perhaps quantum mechanics was not confined to laboratories, particle accelerators, and distant cosmic phenomena. Perhaps life had quietly been using quantum tricks all along. After wandering through black holes, invisible fields, and the strange preservation of information, it becomes tempting to imagine quantum mechanics as something distant from ordinary life, something belonging only to laboratories, to particle accelerators, to mathematicians writing equations beneath fluorescent lights late at night. And for many years, physicists largely thought the same way. The quantum world seemed far too delicate to survive inside living organisms. Quantum coherence fades quickly when systems interact with warm, noisy environments. Decoherence constantly pushes large systems toward classical stability. Life, meanwhile, is warm, wet, chaotic, and endlessly active. Not exactly the ideal setting for fragile quantum behavior, and yet, nature has a habit of surprising us. Over the last few decades, scientists began discovering hints that some living systems may quietly exploit quantum effects in subtle and remarkable ways. Not in mystical ways, not in ways that suspend biology or rewrite evolution, but in ways suggesting life may occasionally borrow useful tricks from the quantum world itself. One of the most fascinating examples involves birds. Every year, countless migratory birds travel enormous distances with astonishing accuracy. Some navigate across oceans, others return season after season to nearly identical locations separated by thousands of kilometers. Long before modern maps or satellites existed, birds were already performing feats of navigation that still seem quietly miraculous. And part of this ability may involve sensing Earth's magnetic field through quantum processes occurring inside their eyes. Researchers studying certain migratory birds discovered proteins called cryptochromes, found within retinal cells. Under specific conditions, light interacting with these proteins may create pairs of quantum entangled electrons whose behavior becomes subtly influenced by Earth's magnetic field. In other words, some birds may literally perceive aspects of planetary magnetism through delicate quantum interactions. Not consciously in the way humans read maps, of course, more like an additional layer of sensory guidance woven softly into instinct. Imagine invisible rivers flowing across the planet, and tiny living creatures quietly learning to follow them beneath the stars. There is something deeply beautiful about that image. Life navigating through quantum whispers hidden inside sunlight and magnetism. And birds are not the only possible example. Photosynthesis, the process allowing plants to transform sunlight into usable energy, also appears surprisingly efficient at the microscopic level. Inside certain photosynthetic systems, energy may move through molecular structures in ways that resemble quantum probability exploration. Rather than following one rigid path step by step, energy may briefly sample multiple possible routes before settling into the most efficient one, not unlike water naturally finding the easiest path downhill, or roots spreading through soil in search of moisture. Quantum behavior, if present, may help living systems guide energy more efficiently through microscopic environments. Again, this does not mean plants are thinking quantum thoughts or consciously manipulating physics. The actual biology remains grounded and subtle. Nature simply appears capable of evolving structures that benefit from the probabilistic behavior already present in the microscopic world. Life adapts to reality as it exists, and reality apparently is quantum. There are even hypotheses involving the human sense of smell. Some researchers have explored whether odor detection may involve not only molecular shapes, but also subtle quantum vibrations helping receptors distinguish different compounds. The evidence remains incomplete and debated, but the idea itself reflects a growing realization within science. Quantum mechanics may not remain locked away inside sterile laboratories. It may quietly participate in ordinary biological processes all around us. And still, caution is important here. Quantum biology remains an active and developing field. Some proposed effects are strongly supported, others remain speculative or controversial. Scientists continue debating how widespread or significant quantum processes truly are inside living systems, and that uncertainty matters. Because the goal is not to turn quantum mechanics into magical explanation for everything mysterious in life. The real beauty of the science lies precisely in its subtlety. Nature does not need mysticism to become astonishing. A bird crossing oceans guided partly by quantum interactions is already wondrous enough. A leaf quietly managing sunlight through microscopic probability behavior is already extraordinary. The universe does not need exaggeration. Reality is strange enough on its own. And perhaps what makes quantum biology feel emotionally powerful is the bridge it creates between scales. Earlier in our journey, quantum mechanics seemed distant and abstract. Tiny particles, isolated experiments, probability clouds hidden beneath ordinary life. But now the boundaries begin softening. The microscopic world touches the living world. Quantum behavior participates, however subtly, in the story of migration, sunlight, energy, and survival. The same quantum rules shaping stars and black holes may also help guide birds through the night sky. There is something profoundly unifying about that realization. The universe is not divided neatly into separate realms, physics here, biology there, cosmology somewhere else. Instead, existence behaves more like a continuous unfolding tapestry. The same underlying laws ripple outward across enormous scales, from subatomic particles to living forests to galaxies drifting through cosmic darkness. And perhaps life itself emerged because the universe possesses this layered richness, a reality structured delicately enough for atoms to stabilize, stars to ignite, chemistry to flourish, and eventually conscious beings to wonder about the strange rules beneath it all. Tiny quantum fluctuations inside ancient stars helped forge the heavier elements in your body. Microscopic interactions inside molecules help sustain the living systems around you. The quantum world is not separate from life. Life arose from it, like waves briefly rising from a deeper sea. And somewhere far beyond living cells and migrating birds, another astonishing connection was waiting quietly in the cosmos. The possibility that the largest structures in the visible universe, galaxies themselves, may have begun as tiny quantum fluctuations stretched across space during the earliest moments of cosmic history, as the strange world of quantum physics slowly expands outward into biology, stars, and cosmic structure. Another realization begins to emerge from the darkness between galaxies. The universe itself may carry ancient fingerprints of quantum uncertainty, not metaphorically, literally. The largest visible structures in existence may trace their origins back to tiny fluctuations born in the earliest moments after the universe began. And to understand how something so enormous could emerge from something so microscopic, we need to travel very far backward in time, back toward the young universe, back before galaxies existed, before stars, before planets, before atoms had fully formed. There was once a time when the observable universe was unimaginably hot, dense, and compressed. Not a fireball expanding into empty space exactly, but space itself rapidly expanding everywhere at once. The cosmos was smaller, brighter, and more energetic beyond ordinary human comprehension. And according to modern cosmology, an extraordinary event may have occurred during those earliest moments, a brief era known as cosmic inflation. Inflation proposes that the universe underwent an almost impossibly rapid expansion shortly after the Big Bang. In an unimaginably tiny fraction of a second, space itself stretched enormously, smoothing and enlarging the young cosmos. To human intuition, the scale of this event is nearly impossible to picture clearly. Imagine a tiny wrinkle on a balloon suddenly expanding until it becomes larger than entire galaxies, or a small ripple on water stretching outward across an entire ocean. Inflation transformed microscopic structure into cosmic structure, and hidden inside the quantum vacuum during those early moments were tiny fluctuations, minute variations, small irregularities emerging naturally from restless quantum fields. Ordinarily, such fluctuations would remain microscopic and insignificant, but inflation stretched them across enormous scales before they could disappear. Tiny quantum ripples became embedded into the expanding universe itself. There is something almost dreamlike about that idea. The visible cosmos may have inherited its structure from microscopic uncertainty. Galaxies, stars, clusters, and vast cosmic filaments may all trace their origins back to delicate fluctuations in ancient quantum fields billions of years ago. The night sky above you may ultimately descend from quantum whispers. At first, these fluctuations were extraordinarily small. The young universe remained remarkably smooth overall. But gravity possesses patience. Over immense stretches of time, slightly denser regions gradually attracted more matter. Gas collected, structures formed. Gravity slowly sculpted the universe like invisible hands shaping drifting clouds. The denser regions became galaxies, the emptier regions became cosmic voids, and eventually stars ignited inside those growing structures, forging heavier elements through nuclear fusion. Carbon, oxygen, iron, calcium, the ingredients necessary for planets, oceans, and living systems, all emerging from amplified quantum fluctuations stretched across the infant cosmos. You can almost feel the scale collapsing inward on itself, the microscopic shaping the astronomical, quantum uncertainty becoming galaxies, probability becoming stars, stars becoming chemistry, chemistry becoming life, and life eventually becoming conscious enough to wonder where it all came from. Modern observations strongly support this remarkable picture. One of the most important pieces of evidence comes from the cosmic microwave background, faint radiation still filling the universe today, left behind from the early cosmos, long before stars fully formed. When scientists map this ancient light carefully, they discover tiny temperature variations spread across the sky, minute fluctuations, ancient density ripples frozen into radiation. These patterns align astonishingly well with the predictions of inflationary cosmology and quantum fluctuations. The early universe still carries scars from its quantum beginnings, like faint fingerprints pressed into cooling glass, and over billions of years, those tiny irregularities evolved into the immense cosmic web now stretching across the observable universe. Galaxies do not distribute themselves randomly through space. Instead, they form vast filaments, clusters, and interconnected structures separated by enormous dark voids. The universe resembles a kind of cosmic lacework, an intricate web slowly woven by gravity from tiny primordial fluctuations. There is something profoundly moving about that image, the grandest structures in existence emerging from minute uncertainty, not despite quantum randomness, but because of it. And perhaps this realization softens the boundary human beings often imagine between the microscopic and the cosmic. Quantum mechanics is not merely the physics of tiny particles hidden inside laboratories. Its consequences ripple outward across the entire visible universe. The stars overhead, the galaxies drifting through darkness, even the large-scale structure of space-time itself may all carry traces of ancient quantum behavior. The universe remembers its smallest beginnings, and emotionally there is something strangely comforting about that continuity. Human beings often feel small beneath the night sky, temporary creatures standing briefly beneath vast cosmic distances. But quantum cosmology reveals another perspective. You're not separate from this unfolding story. The calcium in your bones was forged inside stars shaped by gravitational structure that emerge from ancient quantum fluctuations. The atoms inside your body trace their history backward through galaxies, through inflation, through the restless fields of the early universe itself. You are, in a very real sense, part of the long unfolding of quantum possibility into cosmic structure. Like a wave arising briefly from a much older sea, and still, despite all these extraordinary discoveries, some of the deepest questions remain unresolved. Quantum mechanics describes the microscopic world with astonishing precision. General relativity describes gravity and cosmic structure with equal brilliance. Yet the two theories still resist full unification. The universe continues withholding some of its deepest secrets, and perhaps that lingering incompleteness is fitting, because after travelling from uncertainty to stars, from quantum ripples to galaxies, we arrive at a final realization waiting quietly beneath everything we've explored. The mystery was never a flaw in reality. It may be part of reality itself. After wandering through uncertainty, superposition, entanglement, invisible fields, black holes, and galaxies born from quantum fluctuations, we arrive at the quiet edge of something difficult to name. Not an answer exactly, more like a feeling. The feeling that reality may be far softer, stranger, and more layered than human beings once imagined. For centuries, science was often described as a gradual removal of mystery, a process of replacing darkness with clarity, question marks with equations, unknowns with understanding, and in many ways science truly has illuminated the universe magnificently. Human beings learned how stars shine, how atoms form, how planets move, how light behaves, how galaxies drift across cosmic space. But quantum physics introduced something unexpected into that story. The deeper we looked, the less reality resembled a perfectly rigid machine. Certainty dissolved into probability. Particles became waves. Empty space became active. Matter became vibration within invisible fields. And observation itself became strangely entangled with outcome. The universe did not become meaningless. It became more subtle. Perhaps that is one of the most important emotional lessons hidden inside quantum mechanics. Mystery is not necessarily the opposite of understanding. Sometimes mystery survives inside understanding itself. Even today, modern physics still contains profound unfinished questions. Quantum mechanics describes microscopic reality with astonishing precision. General relativity describes gravity, space-time, stars, and cosmic structure equally well. And yet the two theories remain difficult to fully unite. Physicists continue searching for a deeper framework sometimes called quantum gravity, a theory capable of describing both the quantum world and space-time within one coherent picture. But no final answer has emerged. Some researchers explore string theory, others investigate loop quantum gravity or entirely different approaches. Elegant mathematics stretches toward hidden possibilities. Experiments continue probing deeper into reality's structure. and still the universe remains partly veiled, like mountains hidden behind evening mist, visible enough to inspire awe, distant enough to resist complete certainty. There is something strangely human about that. For all our intelligence, technology, and scientific progress, we remain finite creatures trying to understand an apparently infinite reality. Our brains evolved beneath ancient skies on a small rocky planet orbiting an ordinary star. Nothing in human evolution prepared us intuitively for curved space-time, probability waves, or quantum entanglement. And yet we reach toward them anyway. That reaching matters, perhaps more than certainty itself. Because science is not merely a collection of answers. It is also a way of listening carefully to reality, even when reality refuses to behave the way we expected. Quantum physics repeatedly teaches humility in that sense. The universe is not obligated to fit neatly inside human intuition. Time may not flow exactly as it feels. Particles may not possess fixed properties before measurement. Space may not be truly empty. Matter may not be fundamentally solid, and reality itself may contain layers forever partially hidden from complete observation. But rather than making existence cold or meaningless, there is something quietly beautiful about that incompleteness. Imagine listening to distant music drifting through an open window late at night. You cannot hear every instrument perfectly. Some details remain softened by distance. Yet the partial mystery is part of what makes the experience emotionally powerful. If every note were isolated and dissected completely, some of the atmosphere might disappear. The universe feels similar. Science allows us to hear the melody more clearly, while still leaving room for wonder inside the music itself. And perhaps that is why quantum physics continues capturing the human imagination so deeply. It touches something ancient beneath us, mathematics. The realization that certainty is not always the deepest truth available to us. Sometimes probability lies underneath. Sometimes ambiguity remains unavoidable. Sometimes reality itself behaves more like overlapping waves than sharp-edged objects. And still, the stars shine. Life continues. The universe unfolds. There is comfort in that too. The cosmos does not require complete human understanding in order to remain beautiful. Galaxies drift silently whether or not we fully comprehend quantum gravity. Forests continue growing. Oceans continue breathing against shorelines. Light from distant stars continues crossing unimaginable distances through space before finally reaching human eyes. Reality remains generous even in mystery. And in a strange way, quantum physics may even soften the old boundary between observer and universe. You're not standing outside reality studying it from a detached distance. You're part of the same unfolding cosmos you're trying to understand. The atoms inside your body were forged inside stars. The stars emerge from galaxies shaped by ancient quantum fluctuations. Your thoughts arise from matter, organized into temporary living patterns capable of reflecting upon existence itself. The universe became conscious enough to ask questions about its own nature, like waves briefly becoming aware of the ocean beneath them. And perhaps that is enough. Not complete certainty, not final answers, but participation in the unfolding mystery itself. Earlier in our journey, we began with the old image of the universe as a giant clockwork machine. Predictable, definite, solid beneath the surface. But quantum physics slowly transformed that picture. The clock became softer. The gears dissolved into fields and probabilities. Reality blurred gently around the edges. And beneath everything, beneath particles, stars, emptiness, and space-time itself, we found patterns continuously emerging from uncertainty, like ripples spreading across dark water. Not chaos, not randomness without structure, but possibility unfolding into form. And maybe that is the most peaceful way to leave tonight's journey, not with the feeling that reality is broken or unknowable, but with the understanding that existence may simply be deeper than certainty alone can capture. The universe may never become fully solid inside the human mind, and perhaps it was never meant to. Like mist over a quiet field before dawn, like music fading softly into silence, like distant starlight arriving after millions of years of travel, reality remains partly unresolved, beautifully so. And so, we've reached the end of tonight's exploration. Whether your eyes are still open or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe or share this with someone who could use a peaceful pause. Time has a way of slipping through our fingers, but here, in this quiet moment, it's just you and the soft hush of rest. Sleep peacefully, wherever and whenever you may be.